Thank you so much.
There's a few thumbs up, so look
Yeah,
like
I can. Looks. Yeah,
they
it
can
seems.
hear
It
it.
seems. Yeah, they can hear us.
Yeah,
It's good. It's a good
which is
sign.
good.
So yep. All right. So we still have lots of guests here. How's the weather there, by the way, Dr. Peter?
Today is not very good. I mean, it's a bit cloudy, a bit of rain, but nothing
Mm-hmm.
very serious. So compared with what's happening in the other part of Australia, I mean,
Mm-hmm.
we are quite spared from
Mm-hmm.
that perspective. So just some really light
Mm-hmm.
rain that we have. Yeah, but it's cold. It's winter here, so
I see. Okay. Yeah, because here from my end, I'm actually based in the Philippines right now. So from my end, it's
okay.
like yeah, yeah. So I'm
How's the
actually based
weather?
in the. It's actually raining right now. Heavily raining from my end, but you cannot hear that because I'm in a closed room. But yeah,
Yep.
it's been heavy. I mean, raining, starting to rain. Like a few weeks ago, we experienced same thing, but eventually it stopped and then it came back again. So yeah, the weather here in the Philippines is unpredictable.
Yeah,
So yeah,
but
okay, all
but
right.
you your
Okay, thank you so
summertime,
much.
isn't it, at the moment?
Yeah, it's actually yeah, summer. No, today it's no, it's not summer. It's actually towards December. It starts to get wet. I mean, raining. So
The wet
yeah,
season.
right. Yeah, the wet season. It's during Christmas usually. So yeah, that's until January. And oh yeah, I
Okay.
guess February, Chinese New Year.
All right.
Alright.
I know where to come if I need to find the time to come to Thailand. I'll pick the dry season, not the wet season.
Yeah, the dry season. Yeah, yeah. It's good. Most of the summer, I think, March to May here in the
Yeah.
Philippines. Yeah, but sometimes it changes because of the weather's again, it's unpredictable here. So yeah, but
Yeah.
usually it's between March to May. All right, thank you so much everyone for sending up your thumbs up and for confirming that you can actually hear and see us and view the screens. All right, so yep. Um, Maybe we can, I'm not sure, Dr. Peter, maybe we can start the presentation perhaps. We're 5 minutes earlier than what is expected.
Yeah. I'm happy
Okay.
to start earlier, but it
Y-
look like we still have some people that are waiting, isn't it? We need to
Yeah,
admit all the other people first.
n- yeah, I already accepted everyone. So,
Yeah.
yep. So, yep. Anyway, I will still be accepting those who wanted to join us while you're presenting. I'll work it out from my end, Dr. Peter, while you're presenting. So just focus on. I mean, just focus on the presentation. Everything else, I'll do
Okay.
it for you. Okay.
No
So
problem. Thank you so much. Yeah.
no problem at all. So yeah, let's just let me put my. Okay. I don't know. All right, so yep. Good morning, everyone. Good afternoon, and this is Marvin. Okay, I'm one of the course advisors here at EIT. I've been working here for almost 2 years now, and today I'll be hosting this webinar together with Dr. Peter Wong. And yeah, so basically, yeah, just a sec. Can you see my screen, guys?
Yes.
Okay,
Yeah.
yep. Okay, cool. So, yep. Let me just see. I think there's something wrong with my. Okay, just a sec. All right, cool. So yeah, just a little bit of housekeeping. So we would like to we would like everyone to have a laser focused attention on this presentation because I mean this webinar because this is a technical topic webinar. So we would like to request everyone to please turn off your notifications. As you can see on your screens, there's an instruction on how to turn it off or disable. Please follow it. And of course, and at the end of this presentation, we will have a short Q&A session. We will be answering all those technical questions that you may have. And of course, you can also put them on the chat box if it's something to do with EIT and some of our courses. Okay, so yep. For common questions, FAQs. So for those who have registered, everyone will receive a copy of the slides and the video recordings of this webinar. So please expect them on your emails for within the next 2 business days. So kindly monitor your junk mails as well because it usually goes straight there. And of course, since this is a technical topic webinar, for those who stay tuned until the end of the presentation, we will be providing you a certificate of attendance for this one. So basically, we will be posting the link as well as the QR code at the end of the presentation. All you have to do is scan that one. It will direct you to the survey. And after filling out the survey and filling out the form, you will receive your certificate of attendance in the next 4 business days. Okay, so yeah, a little bit of EIT. So for everyone, so for those who have just first time they have attended first time here with our webinars. So about EIT, so we are an engineering school based in Australia. So we have campuses in Perth, Melbourne, and we also have recently opened our Brisbane campus. So we specialize in engineering courses, guys. So we offer wide range of programs. We have our professional certificate courses, which is a 3-month course good for upscaling. We also have our diploma and advanced diploma courses. We have our undergraduate certificate courses, which is a 6 months course. We also have our bachelor's degree. We have our graduate certificate, graduate diplomas, masters, up to Doctor of Engineering. So these programs are industry-oriented programs, which means after completing the course, of course, it provides value. Okay, so we make sure that at the end of the course, at the end of your studies here, you'll be able to use this one valuable to employers. Okay, and not just employers, but if you'll be practicing, it will be very valuable for you as well. So our some of our courses are accredited, or we have our accreditations here. So our programs are nationally recognized by the Australian government, and we also have our programs are accredited by Ingenious Australia and internationally recognized under 3 accords, namely Sydney, Dublin, and of course Washington Accords. So these programs are being delivered by our industry experienced lecturers, which means they are experienced engineers, and of course subject matter experts. So we make sure that you'll be able to get the knowledge, the skills from these experts. You'll be able to use once you complete the course with us. So we're making use of a unique delivery model. We're using live webinars, state-of-the-art workshops. We also have our dedicated learning support officers, and as well as using our virtual and remote laboratories. Okay, so yep, that's it. And so yeah, this is the most common question I've heard from why students choose EIT. So in the past years, like 2021, 2022, and 2023, so based on the survey that Kilt did, we ranked first on a overall satisfaction in postgraduate students overall postgraduate engineering programs. We also have a rank one in terms of the graduate for as Australian provider for graduates in full-time employment for undergraduate engineering programs. And on those years, we also top rank part of the top 3 in terms of quality of education experience for undergraduate engineering programs, as well as student support. Yes, we have a very good support here for our postgraduate engineering programs as well. So we rank on those for top 3. Okay, and in 2024, we've been awarded as an Australian Export Award for International Education and Training. And same year, we've been awarded as well as the 2024 West Australian Export Award for International Education and Training as well. So for both Australian and West Australian, we received those awards. Okay. So, yep, without further ado, let's do the webinar. So today's topic would be Introduction to Optimal Power Flow in Australian Electricity Distribution Network. This is a technical topic webinar which will be presented to us by Dr. Peter Casey Wong. He is actually one of our EIT lecturer here, and then at the same time, he is the director and principal consultant of Eagles Engineering Consultants Pty Ltd. So I will give the floor to Dr. Peter Wong to, um, you know, um, introduce himself to us. Dr. Peter, would you be able to share a bit about you to our audience today?
No problem. Okay.
So you can take control, Dr. Peter.
Okay. Okay. All right. Good morning or good afternoon, depending on where you are. Um, I guess I mean the Australian has got a way to deal with the different time zone. We greet one another as good day. So when I say good day, it covers both your morning and your afternoon. So thank you
Yep.
for taking the time to attend this webinar. I'm Peter Wong, so I have worked in both Hong Kong and also the Australian supply industry since 1983. I run my own consulting practice. I'm the director and principal consultant of Eagles Engineering Consultants. I've got a website, so you could actually go into it if you want to know a little bit more about what my consulting practice is. But most important, I guess, I have been working in the electricity distribution industry and a lot of time in Australia for the last 25 years in various asset management roles. So I've got a diploma, I got a bachelor degree from the University of Hong Kong, some leadership um, qualification, and also a PhD degree from Victoria University in Melbourne. My PhD thesis is on smart distribution voltage control in the presence of intermittent PV generation. So renewable generation is very much close to my heart. And I guess the topic that I've chosen today on optimal power flow, it's certainly one of the key applications that we use to analyze the situations with renewable generations in the distribution network. So that's what I would be focused on today. Now, we do have a question and answer sections at the end of it, so I would like to leave the questions that you might have, if you can put it into the chat, but I would try to address them at the end rather than actually during the presentation. Okay, so the agenda today, I'll talk briefly about what is optimal power flow and the types of
Dr.
OPF.
Peter, Dr.
Yes,
Peter, would you be able to take control of the slides? It's
uh,
yeah,
I
and
am
up.
doing it. Okay,
Yep.
I thought I'm doing it. Hang on.
Yeah,
Let me. What did
sure.
I need to do?
It's on
Uh,
the upper side.
share. Is it
No, it's not share. It's take control. It's on the upper side of your screen.
upper side of the screen?
There's a take control button there.
Uh, control. Uh, with, oh, okay. Yes. Sorry. Yep.
Okay. All
So
right. Thank you.
can you see my screen now?
Yes, I can see your screen now. Thank you, doctor.
Okay. All right. So the agenda today is I'm going to talk briefly about what optimal power flow is and the type of OPF. I won't be going into a lot of the mathematics behind or formulas behind OPF. What I would do is I'll actually give you a few references at the end of the presentation in the chat box that if you're interested in looking at the formulas and the mathematics, you can actually go into it. I will be more focused on looking at use cases for OPF, talking briefly about what is OPF used in electricity transmission, and a lot more time spent on the use cases for OPF in electricity distribution. And I want to give you a detailed case study in terms of how OPF is actually used to determine what we call dynamic operating envelopes, DOE. And I would talk about apart from the use cases, what are the challenges in using OPF in calculating DOE? What are some of the research that, if you're coming from a research background, what are some of the research that would be required to improve the way that we use OPF in distribution networks? And lastly, as I mentioned before, I'd like to be able to discuss with you or answer any questions that you might have. Okay, so what is optimal power flow? Uh, Now, I think if you come from an electrical background, you know what power flow is. Power flow simulation is basically a way that we're trying to determine the voltage and power flows in a power system network. For example, I mean, I saw the formula here. Depending on how many buses that you have on a network that you're representing, then basically the P and the Q, the active power and the reactive power would be determined based on the voltage on the sending end and the receiving end of the bus, and then you've got also the phase angle that you need to take into consideration as well. So you can see the power flow equation is relatively complex because it involves both sine and cosine functions, and also products of voltage magnitudes and angles, which means that power flow simulation of the power flow equation are generally what we call nonlinear. So when you solve the equation, it's relatively complex and iterative that you need to go through, and even having power flow simulation and try to do power flow simulation in a very quick time frame. It's already a bit of a research topics that are still ongoing at the moment. So of course, with the advent of a modern computer, we find that they can be solved, but it could still take a bit of time, quite a bit of computing power to actually do such powerful simulation. Optimal power flow is adding another layer on top. So optimal power flow, of course, is still power flow simulation, but it aims to optimize an objective function. So apart from solving a P and Q equation, it's trying to optimize an objective function, and you can define what the objective function is. For example, you could be minimizing the generation cost, you could be minimizing the power losses, or you want to maximize the voltage stability. So you are solving the power flow equation, but at the same time, you actually try to look at a process where you try to maximize an objective function, which essentially means that it's actually going to be even more calculations that we're doing. So for each of the scenario that you're looking at, you will have to solve the power flow equation to look at the power flow, and then you determine the losses, and then you change, for example, you change the generator's configurations, and then you run the power flow again, and then look at the losses again. And because you try to minimize the losses, so optimal power flow is actually another layer on top of the powerful simulations with a certain aim that you're trying to do. Now, so what type of OPF do we have? The one is there is a few OPF, optical power flow, optimal power flow. One is called the AC optimal power flow. AC standing for alternating current, and basically it's solving the nonlinear AC power flow equation as they are. So which is going to be very accurate because you're not doing any simplification, but computationally would become complex. As I mentioned before, the power flow equations are nonlinear, involving both voltage, phase angle. So when you take those into considerations, the solving of those is actually quite computationally quite complex. But most accurate way of doing it. The other one is what they call DC power OPF. DC standing for direct current, but in effect, I think it's actually more correctly described as what we call a linearized OPF. So it's not really a DC, it's still an AC simulation. But what we try to do with the linearized OPF is actually to simplify it by assuming that the voltage is about 1 per unit of each of the bus. The phase angle is relatively small, and therefore, when you look at this equation, you simplify the equations by removing the reactive power flow equations and also the corresponding variables and constraints. And therefore, on that basis, it's less accurate, but it's run a lot faster. And I would talk about why running a lot faster is actually important, especially in the distribution network applications that will become quite evident later on when we look at the use cases of OPF. So just remember that linearized OPF or DC OPF is probably going to be more useful from a distribution network perspective because of the execution time. Apart from the AC OPF and DC OPF, we also have what we call the security constraint OPF. So, and this what this does is that it basically includes contingency. For example, one line out, one transformer out. So you want to be able to look at those power flow in a way to look at the system reliability, maximize system reliability. So that's for security constraint OPF. And the other one is what they call those stochastic or robust OPF, which look at uncertainty in demand of renewable generation. So this is obviously quite important when you start to look at the uncertainty associated with both electricity demand and also the uncertainty associated with renewable generation like wind and solar. So stochastic OPF, it's very important in that regard. But of course, I mean, once you take into account of certainty, probability type of distribution, again, I mean, it's complex. It makes the calculation a lot more complex. So with this quick sort of summary of OPF, let's look at what are the use cases for OPF. Now, OPF certainly start as an instrument, as an algorithm that is commonly used in transmission systems. So when you have transmission system, one of the very common application of OPF is basically looking at for a transmission system operator to schedule generation resources. So when you have got a number of generators that you can connect to the network, whether they are fossil fuel generators, um, gas turbine, hydro generators, or renewable generators, you the operator will try to schedule those generators to meet the low demand, but at the same time, you want to minimize, for example, costs. So this is what we call economic dispatch problem. So and the equation that you're trying to look at is that obviously the power has to balance. The power that is being produced by the generator need to be balanced with the load, unless you've got storage devices that you have on the network. But even if you've got storage, you still need to balance the storage as a generations or as a demand. But at the end of the day, the generation and the demand would still need to be balanced. So you've got the power balance equations, you've got the generator limits. That you will have to consider. There is also voltage limits, decay voltage limits that you have, and then you try to make sure. So the economic dispatch, you want to minimize the cost, but you are subject to the constraint of power balances. The power need to be balanced. The generator, the voltage limits need to be adhered to. And if you got lines, you want to make sure the lines are not overloading through that process as well. So economic dispatch is a very common applications of OPF in transmission application. But remember today, I'm not really so much focusing on transmission. We actually see a lot more of OPF being applied to distribution networks, which traditionally wasn't really the case. And the reason is if you look at distribution networks in the past, OPF is less applicable because distribution network tend to be mainly radial. That means you have unidirectional power flow, which follows the law of physics, basically the less resistant path, that's where the electron flows. And the loads were very passive, so it's not flexible consumptions. The loads are just, when people, with cooking, when people actually switch light on, that's when the demand comes on. But OPF is certainly finding more application these days in electricity distribution networks. And that's because of the rise of distributed energy resources, what we call DER, which can be solar, it can be battery, it can be wind, it could be electric vehicles. It could also be more controllable loads now that we have, for example, electric heating, where you could potentially be controlling that electric heating or the cooling, making use of the thermal capacity that you can sort of hold within a building envelope, for example. Now, so apart from having generation and flexible load, the important thing is that there is also what we call the ICT, the information and communication technologies that overlay on top that allow the monitoring and the control of these resources. Now we have a term for this, and you might have heard about it already. We have a term, we call it the smart distribution grid or active distribution grids. So you've got an ICT, which allows you control and monitor, and then you've got something that you can actually control and monitor in distribution networks. Now, with a smart distribution grid, where you actually have got embedded generation, distributed energy resources generating within the distribution network, not coming from just from the transmission systems, it's possible for some sort of a system operators to look at optimizing the operation of DER to meet a multiple objective function. For example, you can use those DER for generation dispatch. So the economic dispatch problems that we mentioned in the previous slide could now be extended to cover distribution network. Because even though the distributed energy resource individually by itself is very small, but when you combine them together, they can actually operate like a power station. So that's what we call a VPP type of setup, a virtual power plant setup where an operator basically aggregate all these resources, small one, but when they aggregate together and having the control to dispatch them, you can actually treat them as a power station embedded in a distribution network. So it can actually be used for generation, but also you can actually support the network as well, the distribution grid, in terms of providing reactive support, for example, for voltage optimization. So once you go into a active distribution networks with all these new resources that we have, and especially distributed engineering resources, it become more more applicable for OPF to be applied to a distribution networks. So what are some of the use cases that we can actually see with OPF being applied in distribution networks? So what are the use cases? The first one, I think, which in the previous slide alluded to already, you can use it for voltage regulation. So what is the goal of OPF? Is to maintain the voltage with acceptable limits. For example, plus or minus 6% of your nominal voltage, depending on what the nominal voltage is. And the OPF use case in this case is that you will coordinate the tap changes, the capacitor band, the DR reactive control to regulate the voltage that you have on the network. So you basically now you're running power flow, but you actually try to in this case maximize your voltage to have the best voltage that you have in the networks. So examples of OPS use cases could be in networks with rooftop solar PV system, photovoltaic system. OPF will reduce the overvoltage during midday by adjusting the inverter set points, for example. So when you have a voltage rise, when a lot of generations are happening on the distribution network, not much low, you can actually use OPF to determine what the appropriate settings that you can have with whatever equipment that can actually provide a reactive support. And this is quite interesting. If you operate in the electricity industry, you probably have heard about it in April this year, end of April this year. There is actually a big blackout affecting Portugal, Spain, and a small part of France. And it was attributed to inadequate voltage control by the system operator, because in that network that they have over there, they have a lot of renewable generation. So they got a lot of solar, they got a lot of wind. And when those are operating, they actually displace the conventional generators. We can provide reactive support, whereas the renewable generation actually hasn't got much reactive support capability. So because they haven't really look at that aspect or haven't controlled it well, we have end up with a voltage rise and then a cascaded total failure, which end up with a blackout that actually happen. So you can see OPF can serve a very important function in managing the voltage that you have on the network by being able to control the resources that you have on the distribution networks. Of course, another use case for OPF in distribution networks to minimize technical losses, which is really similar to what happened on the transmission network. You can run it in a way to look at reducing the technical losses. And that a lot of cases means that you try to use the generation that is close to the load. So instead of having the generation coming from a far away central power station, you try to dispatch the generator that is actually closest to the load, and therefore you reduce the path that the electricity has to transmit, and therefore reduce losses. So that's another use case of OPF where you run low flow, but with the objective function to minimize technical losses. Now you can also use it to do DER coordination, distributed energy resources coordination. So you can use it to coordinate the different type of DER they have a network, whether it's solar, whether it's battery, whether it's electric vehicles. So again, I mean, using this, you might be able to reduce or postpone the need to upgrade your distribution networks. Voltbar optimization is quite similar to what we described in voltage regulation, but in this case, I think it's really looking at how you can actually improve voltages. And I've got a schematics on the right hand side that show the setup for a Voltbar optimization. Obviously, they can take different forms. In terms, depends on what you have in terms of voltage control device on the network. But when you have those devices, you can run OPF with an objective function to try to optimize your voltage that you have on the network, by using OPF. Now, there are other usage cases as well. For example, we can also use it to manage congestion in distribution networks. So when distribution network, the lines and cables are overloaded, you can actually use OPF to determine how you can actually, again, use the local generation resources or flexible loads that you can reschedule to reduce the overload, and therefore in some way you maximize the utilization of your distribution network before you need to spend a lot of money to upgrade the network. It can certainly be used in fault recovery and service restoration. So you can actually look at what's the best feeder configurations when you've got when you have got a supply interruption, one of the feeders out, how you can actually restore and with the minimal load interruption that we still need to have. So you can also use it from a tariff perspective in terms of optimizing time of use. So you've got so you can actually use it to shift, or you can change the load shape in some way to reduce peak demand and also reducing costs. So again, I mean, what is important to look at is that it's power flow, but it's actually the objective function, how you formulate the objective function for the different applications. Hosting capacity is the other application. I don't know whether you have heard about hosting capacity, but hosting capacity is really more looking at the capacity of the network to host renewable generation. That's more it normally use or distributed energy resources. In Australia, we got a lot of rooftop solar, for example, and because there's so much rooftop solar, we actually find that we can't take everyone on board, and therefore the hosting capacity, being able to determine what's the maximum that you can take is quite important because it actually allows you to schedule, allows you to connect different type of resources and give them some limits, in terms of what they can actually do depending on the network capacity at any point in time. I'll go into a little bit more details with this later on when I look at the use cases of dynamic operating envelope, which is quite related to hosting capacity assessment. Microgrid, you probably have heard about it. Again, I felt a diagram in terms of microgrid. So microgrid is basically a network by itself and is connected to the utility grid through an interface point. And the interface point could either be connected, which means that the utility grid share the supply of electricity to the local network, but it can also be a situations where the utility grid is connected, and therefore you are basically supplying your own load within the local network. So and then again, I mean, in microgrid, you can look at how you can use OPF to reduce the cost while staying resilient during outages. And then the other one, this application that we have is distribution market operations. So if you want to look at peer-to-peer energy trading, dynamic pricing, and all these, and looking at the effect of how that can how that affect the network. So again, I mean, you can use OPF to do that. Now, this is only really on a very high level to talk about how OPF is being used on distribution networks. And I think to really get more information regarding how is actually, I want to go into a bit more detailed case study, which is not to do with what we call dynamic operating envelopes. So again, I mean, there's a couple of references that I will put into the chat later on if you're interested in looking at what dynamic operating envelopes is and want to really go further into it. But I'll do a very quick overview here, a more detailed application of OPF in determining what we call network dynamic operating envelopes. Now, this is certainly in the context of Australia, but it might be applicable to you as well, in your own countries. Australia is quite unique in the world from the perspective that we have a lot of people adopting solar system. And the Australian government is certainly encouraging it because we have adopted renewable energy in order to meet the zero emission target by 2050. So the Australian government has signed on to the net zero target by 2050. And because of that, they are putting in different type of incentive to encourage both renewable generations connections and the use of renewable generation. So we definitely have got a lot of wind farm and also solar farms. So these are very big, wind turbine and solar system that are connected to the transmission networks. But what is really unique about Australia is that we also have a lot of residential customers because most of the people in Australia live in detached houses with a rooftop. So a lot of the Australians have installed rooftop solar photovoltaic systems. In fact, we believe we have got Australia's the highest per capita concentration of rooftop solar PV, averaging about 1 in 3 households. So 1 in 3 houses actually has got solar PV installed on the roof, and the system is growing. Now these systems are relatively small by themselves, so probably around the 5 kilowatts, 6 kilowatts, some might be 10 kilowatt, but they're relatively small. But once you take into account that there is actually a lot of these on the network, then you can see that they are becoming significant. What I'm showing in this figure here, apart from a photo that show a rooftop solar installation, you haven't seen one before, is a forecast that is done by our system operator called AEMO, Australian Energy Market Operator. So they're forecasting what is going to happen in the next up to 2050. And what they're basically forecasting is that the rooftop solar and wind, is going to contribute significantly to the generation mix as we go into further into the future, as fossil fuel, coal-fired power station, and also gas-fired power stations start to decommission. We're going to be filling those gaps in, using renewable generation sources. So as a matter of fact, we believe that right now, when we add all these renewable generations together from a capacity term, they already are bigger than what is available through the central power stations, and certainly into the future they are going to occupy a very high percentage. Now, so with the increasing number of electricity distribution solar system that we have on the rooftop, a lot of our distribution substations, when I talk about distribution substation, I'm talking about those substations that convert the medium voltage, for example, 22 kV into 400 volt to supply to the customer. A lot of those distribution substations are behaving like generators now during the solar peak generation period. So instead of seeing low current going through those transformers supplying, it's actually the solar systems installed by residential customer pushing the power back into the medium voltage and transmission network during daytime when a lot of people are not using the generations. Therefore, the surplus is going back into the network. Now, so because of that, and quite well-known issue that we know with solar system generations pushing to the network, the voltage would generally goes up. So and the voltage, of course, cannot go up indefinitely. It needs to be within a certain bounds. So for residential solar PV installations, we have to curtail because there's so much of it. So and one of the way to curtail it is through the use of what we call dynamic operating envelopes, and I'll explain what that is. So DOE is a way to manage a lot of solar export that we have especially on the low voltage system that we have pushing back into the high voltage system. So before we talk about dynamic operating envelope, let's talk at what operating envelope is. So operating envelope basically represents the maximum import and export limit at residential connection. So for each of the connection, there's an operating envelope. The maximum. So if we talk about operating envelope for import, that means how much load that you can put on, and if it's the maximum export limit, then it's basically how much the export they can actually take into the network. Now the limits are based on a number of factors. It's based on our voltage, to make sure that the voltage is between the regulation limit. And in Australia, the low voltage is between 216 volt to 255 volt, 253 volt in Australia. And also there is also asset rating as well, the thermal limits, reverse power, for example. I mean, the asset like distribution transformer, some might have a limited reverse power capability, and certainly there is also thermal overload as well, that the generation could overload. So you have got these limits that we have, and this limit would define how much each of the customer can actually import or export from the electricity network. Now, so if we don't have a dynamic operating envelope, then a static operating envelope is probably the proxy that we have. And basically, if you have got static operating envelopes, then the utility will have to determine on the worst case scenario, because because it's static, so you have to cater for the worst case. Whereas if we use dynamic operating envelopes, it would be structured, it will construct it based on the prevailing network conditions. So that means with a dynamic operating envelope, especially from an export perspective, is likely to allow more export into the grid instead of looking at the worst conditions, which is basically maximum generations, minimum load, for example, which might only happen during a very, very short period of time, or not many days in a year. So dynamic operating envelope certainly makes sense. We have done some trials in Australia, in South Australia, for example, the utility there, the South Australian Power Network, what we call second, they did a VPP trial, and they used the DOE as a construct, and they find that they can actually increase the daylight hour average export from the DER, in this case, a rooftop solar, by about 20%. So from 5 kilowatt to 6 kilowatt over the year, and a 60% increase in daylight hour average DER export capacity up to 8 kilowatt during winter months, because winter months there is a bit more load that we have on the network and less generation. So the use of DOE has been proven to be beneficial, and definitely the focus right now from Australia perspective, because we've got more an export problem than the import problem. So we are using export DOE as a way to connect new systems. So when new customers put their hand up, we try to give them a connection agreement, which they got an option. They can either accept a static operating envelope, an export limit, for example, 1.5 kilowatt, or they can accept a dynamic operating envelope, which might give them up to 10 kilowatt export at certain times of the day. So this is a use case. This is actually happening now in quite a few states in Australia where we have got a high rooftop solar generation. But the question that we have is, of course, how do you determine that dynamic operating envelope? How do you actually calculate what is available as an export at any point in time? Especially in the low voltage network, that's when basically OPF comes into the picture. Now, so for DOEs, we definitely need some sort of what we call a network sensing. So you want to know at any point in time whether the network is stressed, what is headroom available for the network to export. So you need some sort of a sensing mechanism so they can know the status of the network at any point in time. You obviously need to calculate the DOE as a DOE, as I said before. OPF is one of the algorithms, commonly used algorithm to calculate the DOE. So you need to do the DOE algorithm. You need a communication between the DNSP, the distribution network service provider, and also the DER. Okay, which in some cases it might not directly to the DER itself, not the rooftop PV, but you go for an aggregator, and an aggregator then have the control over the individual DER. So you need a communication system so you can convey that dynamic operating envelopes to the devices that ultimately need to be controlled. And then you also need to have the DER be capable of setting a DOE. So that means that the export capability coming from the solar PV system, in this case, we need to be able to respond to this limit. So if they receive a limit, say they can give 10 kilowatt, then you would try to pump up as much as you can. But if you're given only 5 kilowatt, then you have to cap it in a way that you won't go beyond 5 kilowatt. So you need to have a DER capable accepting DOE. And in most cases, in the case of rooftop solar, that capability is sitting in the inverter, that connect the solar PV systems to the grids. That inverter would incorporate the functionality to accept DOE. Now, there's certainly a number of algorithms can be used to calculate DOE. OPF is only one of those. I mean, there's other way to calculate DOE as well, but OPF is probably the most accurate way of determining the capacity, the export capacity of the network at any point in time. So I've shown you also a diagram here in terms of the end-to-end setup, how you do the DOE and how you actually go about sending the information to control the inverter that is attached to the solar system. So again, I mean, this is a very simple setup, but this is the structure that we actually use, and this is already in service in a number of DNSPs in Australia. Okay, so we focus on using OPF. How do we determine OPF? How do you determine DOE using OPF? Now, of course, the first thing that you need to look at, you need to have some sort of a network model, because OPF, optimal power flow, is basically a power flow. So to do a power flow, you generally would need a network, isn't it? So for you to do the power flow simulations. So you think generally, and I say generally, and I'll explain that later on. But generally, you need a network model for power flow simulations. You need some simplifications. because when you talk about a power system, depending on how far you go back, and remember we're talking about low voltage here, so those rooftop solar system embedded on a low voltage system. So the low voltage system, obviously upstream is medium voltage, and then you got high voltage, and then you got extra high voltage before you go to the central generators. So if you model the whole, from the central power stations to the low voltage, there's a lot of network that you're trying to model. And that would means that now the power flow is going to be complicated and it's going to take a long time to do. And because you want to have dynamic operating envelope that you can actually convey to the customers, to the end devices to operate on a sort of real time basis, you really can't have the network so extensive, and therefore computation takes a long time. So you need some sort of a simplification basically of the upstream network, because as I say, it's really not practical to model from the power station down to the low voltage customer connection point, because we want the speed of operation. So really a linearized OPF is preferred, because we want to have fast execution. The DOEs are only calculated for customers that are what we call active customers, the customer that actually take up the flexible OE option, because there are some customer doesn't do that. And there's also some existing customer who already have solar PV, and therefore we can't retrospectively go back to them and say that you need to accept a limit now. So it's only for the new customers that's coming on. So you model those, what we call the flexible customers, and you calculate the DOE for them. The objective function in this case, when you do the power flow, OPF, what's the objective function? The objective function is to allocate the available export capacity that you have from the network, but you can allocate it based on different principles. You can allocate it based on equity. Equity means that every customers that participate get the same limit. Okay. For example, if it is, if all the capacity is available is to allocate up to about 4 kilowatt per customer, then everybody get 4. So this is what we call equity. You can also, but the issue with the equity is that generally you find that the customers that are closest to the distribution substation are going to be the one, by the law of physics, that would be able to export more compared with the one that is at the end of the LV feeder. So customer at the end of the LV feeder, if you go by equity type of principle, they're the one that you're going to determine what is going to be everybody exporting. So if the limits at the end of the LV feeder is only 2 kilowatt, that every active customers on that LV feeder is going to be getting 2 kilowatt. Now, obviously, you can see that this is not going to be the best way of maximizing the solar generation. So you can also use an objective function to maximize the volume of export. So in this case, that means everybody will get different, and probably the one that is closest to the distribution substation transformer is going to be given a bigger limit compared with one at the end. So that could be allocated on that basis, or it could be a bit of a combination of both looking at equity and also volume of export. But at the end of the day, this objective function the powerful will still be constrained by the voltage limits that we mentioned before, and also by the further limits that we have on a distribution transformer on the high voltage feeders, for example. So this is how you do OPF to determine DOE, but very important is in terms of how you do the objective function. And again, there's some paper that has been generated by University of Melbourne, who is involved in projects that I was involved in, that look at the equity, what's the best way, what's the fair way of allocating export capacity, and will be quite interesting to look at. And ultimately, I think that is going to be determined by the policy maker. So policymaker will have to make a call regarding what's the best way in terms of allocating it. Are they going to maximize the solar generations, and therefore, from a greenhouse gas perspective, it's going to be good, but disadvantage some local customers, or do we want to look at equity among all the customers that are connected to the same distribution substation? It's the jury is still out in that regard. Now, so what are the challenges in the use of OPF for distribution networks? I talk about a network model. Okay, so. And the problem with the network model is that a lot of the low voltage networks that we have in Australia, we don't really have accurate data for it, because in the past there's not a lot of need to have to capture the LV data. There seems to be a lot more focus on the transmission network, the high voltage network, the medium voltage network, rather than the LV networks. So when you run OPF, if you need a network model and you don't have the data for the LV network, then we have a challenge. So so that's one of the challenges that we have, using a network model based OPF. The other one is the renewable generations are variable intermittent, which means that when you do the OPF, especially when you look into the next hour, the next 5 minutes, the next 30 minutes in terms of what the solar can generate, you essentially need to be able to forecast what the generation actually look like. So, and generations are variable and intermittent, and also the load, the new nodes that we have, like from electrifications, whether it's to do with EV charging, for example, electric vehicle charging, also require a new forecasting approach, for you to be able to actually, have some accuracy in terms of what it look like, looking into the future. Um, and of course, I mean, new market rules, aggregators, new actors that we have on these providing these energy services will also complex it as well, because again, you need to forecast the behavior, and customer response to government and market incentives also uncertain. How many customers are going to pick up electric vehicles, for example, is uncertain. So, what are some of the research direction? This will lead to sort of the end of my presentation. Is that I think there is definitely mentioned before LV network data. If there is no network LV data, then we want to be able to look at, is that possible to do voltage calculation without electric models? In fact, there are successful use of a neural networks approach to basically identify what we call an electrical network free approach to calculate voltages using OPF simulation instead of having a network models. And you can actually look it up, and they have got a patent, IP associated with that approach, and there's even a spin-off company that is now commercially operating from using this approach. So if you're interested, you can look it up. In terms of the forecasting that I mentioned before, the challenges that we have, I believe AI probably has got a lot to do to help in terms of the short-term generation and load forecasting. Definitely a research area. And I mentioned before that you need to basically provide some equivalent network of the upstream network. So equivalent network representation to reduce the OPF execution time, again, would be quite useful. And there's a lot others as well, but I'll stop here basically with my presentation, and we can spend a little bit of time to talk about questions that you might have. Thank you for your attention. Marvin, do you?
Yeah, thank you so much, Dr. Peter, for that presentation. So, yeah, let me just take control of the slides, perhaps. Okay, cool. So,
Yeah.
yeah, for those who are interested in this topic, so this is actually a multidisciplinary topic. It covers electrical and renewable energy engineering schools. So these are the courses that you might want to consider if you're, planning to study with us. We have the professional certificate course of competency in power distribution. We also have the professional certificate course of competency in electrical power system protection, the advanced diploma of applied electrical engineering, electrical system, which runs for 18 months. We also have the professional certificate course in power industry, applied electrical engineering, which runs for 24 months. We also have our advanced diploma course in applied electrical engineering, renewable energy. We also have our online Bachelor of Science in electrical engineering, and of course, our graduate certificate course in power engineering. Okay, so yeah, for the upcoming courses, we have, as you can see on your screens, we have this courses that will be upcoming. So if you need more information or if you need assistance in terms of application, please feel free to reach us here at EIT, and our course advisor team will be happy to assist you with that one. Okay, now let's do our Q&A, short Q&A sessions here, Dr. Peter. We have some few
Yeah.
questions here from
Yeah.
our from our attendees. So let's
Yeah.
have one from Connor. So he was actually asking, when you say that AC OPF takes a long time, how long are we
Mm.
talking in practice to model, and how much faster is the linearized OPF? So that's from Connor.
Yeah, this question is obviously a bit difficult to answer because it depends very much on your network, the size of your network. But what I'll do is I'll answer it from another perspective. If we want to use OPF to basically run to determine dynamic operating envelope, we the way that we use the dynamic operatings in a generation type of scenarios that we would like to be able to do it because the market response is every 5 minutes. So that means you need to be able to provide calculated OPF, convey that information to the aggregator for the aggregator to be able to respond to the market dispatch needs or the bidding in the market, which has to happen within 5 minutes. So from that perspective, we're really talking about being able to do OPF. If you're using it to do dynamic operating envelope, you will really need to be able to do it within 1 or 2 minutes sort of time frame. Because if you can't do it, then essentially it's no use from a market response type of perspective. I don't know whether that gives you an answer, but that's another way of answering your questions.
Thank you so much, Dr. Peter. And we also have one from Andrew Hewitt. He asked, do you need to have an accurate operating parameters for all customer connected inverters to run an OPF simulation on a distribution network? So that's coming
Yeah.
from Andrew Hewitt.
Yep. Andrew, that's a very good question. It depends on whether the inverters are being asked to provide certain support to the network. Now, what I mean is that in Australia, for example, all the solar inverters, especially the new one that are connected, we ask them to support the network by having a VOC-VAR control function and also a VOC-WAT control function. So essentially, we're saying that the inverter are asked to provide reactive support to the network when the voltage is high, and also to curtail real power outputs when the voltage is really high. Now, if that's what it is, then you need to factor that into your OPF calculation so that you know that at this certain voltage that you have in the customer connection point, there would be certain reactive power support coming in from the inverter, and you need to take that into consideration in your powerful calculation. So the answer is yes, if the inverter are asked to actually support the network, but if not, then I guess you'll be looking at the inverter is that it's just pumping out active power, so you're not really concerning about the other aspect of it. So that's the answer to your question.
Right. All right, thank you, doctor. So we have another follow-up question from Andrew as well. So does the DOE calculation include limits for customer connection point voltage magnitude? So that's from Andrew as
Yes,
well.
it does. Yeah, Andrew, it does. When we talk about the voltage, we really talk about the connection point voltage. So you are using the connection point voltage to do when you do the powerful calculations. The utility is focusing on the connection point. We're not really looking at the voltage at the PV inverter terminal, for example. I mean, you're really looking at the connection point to the customer.
All right, cool. Thank you so much, Dr. Peter. I think that's the questions that we have. So we still have time, though. We have still a few minutes left. So if you have any questions, though, please post it in the Q&A section of the screen. Yeah, we can see there are some. Just a sec. All right. So yep. Again, if you have any questions, please post it in Q&A. We still have a few minutes left, and then yeah. Dr. Peter, I remember there was actually a documentary about the Australian, putting a lot of solars
Mm.
on top of the roofs. Can you tell us about it, perhaps? Because I'm really interested about it, though.
Yeah. Well, I mean, it's quite interesting the love affair that Australian has in terms of rooftop solar. I guess it's driven basically by there's a customer incentive because of the way that we want to maximize renewables to meet our net zero target by 2050. So there's some incentive coming from the customer, coming from the government, and mainly in form of either subsidies for the solar panels or what we call the feed-in tariff, more favorable feed-in tariff. When they actually sell the electricity by the grid, they get better. Now, all those changes obviously over the years now, because the solar panel cost has come down. But the other thing I think that's quite interesting to see is that even though Australia seems to be quite unique in that respect, I recently gone to attend a conference, a electricity distribution conference in Europe called CIREC in Geneva in middle of June, and it was surprised to hear that a lot of the customers in Europe are also putting on solar panels now because of the high price of electricity. So because of that, they try to say that no, let's supply my own needs rather than let's supplying it from the grid because the electricity price are going up and up. So even though I think we're still quite unique in terms of the amount of penetrations of solar rooftop, I think that there's a lot more adoptions of solar system now in other parts of the world, including Europe. So that's what I'm hearing from.
Yeah, especially here in the Philippines. But anyway, yeah. So thank you so much for that. Yeah, because I've heard it from a documentary as well that the Australians tend to have these solar panels, and I don't know if I heard it correctly, but I think that's some kind of an issue at the moment there. So I'm not sure if it's still
Yeah.
updated, but I just saw one documentary. So yeah, we have another question here from Takeshi Umizu. So does BESS contribute to the OPF? That's from
Yes.
Takeshi.
Yeah, battery energy storage system BESS definitely need to be taken into account in OPF. So when you run your
Mm,
power flow, if there is actually BESS, then you need to take that
mm,
into consideration. Now, the issue with BESS is that depending on where the BESS is connected, if the BESS is actually connected behind the meter, that means it's installed by the customers together with the solar panels, which is quite common in Australia as well, because they don't want to sell it back to the grid. Now the feed-in tariff is quite low. They want to maximize the self-consumption. So if
mhm,
BESS is actually behind a meter owned by customers, then when you
mhm,
talk about modeling, the question that we have is that how do you model that? How do you predict what the customer behavior is? Would
mhm,
they sell it to the grid or would they actually self-consume? So just put
mhm,
another degree of uncertainty. Now, if the BESS is
mhm,
actually on the grid, is connected by
mhm,
the DNSP or another company connected to the grid, then it's more you probably know more in terms of how it's operating, and therefore you can factor in your power flow calculation. So, but definitely you need to take that into consideration. The question is how, how you're going to do it.
Yeah, that's the question. How? Okay. Thank you so much for that, Doctor. And we have another one from Samson. So questions are actually flowing now. So, are you allowed to sell excess power to the grid if you have installed your own solar PV system? I think this is somehow related to what we discussed a while ago. I'm
Yeah,
not sure.
definitely. That's what we call the feed-in tariff. So you would get a feed-in tariff, the amount that you feed into the grid. But the feed-in tariff, while it started very favorable in Australia, is now very low. So which essentially means that it doesn't make sense now to feed in. It's actually a lot better for customers to self-consume. And of course, I mean, if you can self-consume because you're at home and you can run all the plants during midday, that's fine. But if you don't have, then battery become an option to consider. So you can put a battery, store up the excess one during daytime, and then use it at nighttime when everybody is home. So again, I mean,
So,
yeah.
which
But the
means
answer
the
is
answer is
yes.
yes.
Yeah,
Yeah.
yeah.
All right, cool. Thank you so much. So we have another follow up from Takeshi. So, what is the relationship between OPF and FCAS?
Yeah, the frequency control and scenery service, which is FCAS, definitely. I mean, if you look at FCAS, you could potentially use OPF, but OPF, I mean, for FCAS, which is really more of a transmission stability type of perspective, you tend to think that it's probably not going to be necessarily using OPF. I mean, it would be more in terms of some constraint, security type of constraint. So yes, I mean you can potentially use OPF, and but my understanding is probably OPF is probably less used in that situation. But FCAS tend to be using really more focus on the transmission scenes, and therefore I mean it tend to be more detailed, using more complex type of probably AC OPF. If it is going to be OPF, it won't be the DC OPF that you actually use.
All right, thank you, Dr. Peter Wong. So here's the thing: we will be answering the last five questions here, Dr. Peter, and then we'll wrap up because of the time. So we
Yeah.
have here from Andrew Hewitt. So can power flows be better optimized where distribution entities have dynamic tap control on their distribution transformers? So that's a follow-up question from Andrew
Yeah.
Hewitt.
That Andrew, good questions. And again, I mean, the answer is yes. The more utility have in terms of control over the network, the better. But you're also probably aware, depending on where where you're located, distribution transformer generally hasn't got tap or no tap change control. They normally have got taps, but the tap is offload tap, so you can't change it unless you send somebody out to do it. So dynamic tap control is definitely very useful, but they don't exist in most of the distribution transformers. Now, for new transformer, yes, I mean they could potentially be applied, but the cost of the new transformer is going to be increased quite a bit, probably around 30% more if you have dynamic tap control, and there's also some maintenance aspects that come into that picture as well. So what I can say is dynamic tap control has got its place, probably in some localized area, but I don't see that as a widespread applications across the grid, especially in Australia, because of the cost associated with dynamic tap control.
All right, thank you, Doctor. Here's another one. Is the dilemma of stopping solar feed inequality issues resolved by that low feed in tariff? An example encourages self-consumption only. That's actually from
Uh,
Connor.
yeah. No. I definitely need. There are a number of ways to address that, and one is
Mm-hmm,
actually looking at the solar tariff. That's definitely one option of it. But
mm-hmm,
again, I mean, it all depends on what it is. So it doesn't
mm-hmm.
solve all the problems, but it definitely address part of the
Mm.
issue that we have. Yeah.
I see. All right. Thank you, Doctor. Hope it answers answers your question, Connor. So we have last two here, which comes from Henry. May I know the fiber network used for that grid showed protocol. That's from Henry.
Uh, Sorry. Let me look at the question.
May may I know what the fiber network used for that grid showed? So I think he's
Fiber,
referring to
fiber,
fiber, yeah, network.
fiber network. I didn't talk about fiber network in my
Your
presentation. I
presentation.
don't know
Okay.
exactly. Yeah, I don't know exactly what that
Okay.
question is.
Maybe we can
Yeah, yeah.
we will have a review and get back to you on that one, Henry. So yeah, we have from Shah, Dr. Peter. So he was
Yep.
actually asking, um, yeah, please, that OPF is for radial networks. So any difference in approaches if applying for interconnected networks? How to harmonize contractual obligations payments for KWH export to grid versus equity in the OPF? So you can see these questions, Dr. Peter, in the chat box itself, not in the Q&A.
I'm looking at it now.
Mm-hmm. Yep.
I don't know why I'm not seeing those questions.
And
I
it's
can
on the
see
chat
some.
box. Yeah, and it's under the chat
It's on
box.
the chat. Okay, not Q&A.
Yeah. So no, it's not in the
Okay, okay.
Q&A, so it's in the chat box. I think you
Okay,
have
okay.
no access to the Q&A. Yeah.
Okay. I see that now. So, well, OPF is not just for radio network. Obviously, the use case that I showed you, the OPS is for radio network. You can use it for mesh network as well. It's not that but obviously, when you solve a mesh network, it's going to be a bit more complicated. It's going to take more executions. But OPF is definitely not reserved just for radio networks. Uh, in terms of harmonized contractual obligations, payment for kilowatt hour export to grid versus equity in the OPF. Um, Again, I mean it's quite interesting. I think there is that equity that I mentioned about in OPF. How you allocate the export limit. Uh, the kilowatt hour export. Remember here you talk about there are two types of it because when you talk about a customer that's got a solar system and maybe some sort of battery. When they are giving an OPF, when they're giving an operating envelope, it's not that they are selling it just for a tariff. They're probably selling it to for another service. For example, you might have an aggregator coming in, set up a VPP type of setup to bid into the generation market. And therefore, this is actually an additional payment that customers might be getting in addition to the feed-in tariff. The feed-in tariff is actually coming from the host retailer through the network owner for that. So this is actually an additional payment. So in some way, the two are not the same. And therefore, when we talk about equity issue, it's not the same equity issue that we're talking about here.
See. All right. Thank you so much, Doctor. Hope it answered your question, Shaw. So, all right. Yep. I think that's it for today. So I can still see some questions here, but unfortunately we will not be able to do that now. But we will get back to you in email, so we'll get your information. Thank you so much for that. And yep. Dr. Peter, thank you so much for sharing that information with us for a wonderful presentation. So for those who are asking about the certificate of attendance, here it is. So you can scan the QR code to that will lead you to the survey form, and then afterwards, you just have to fill out the form, and then we will send you the certificate of attendance in the next 4 business days. So I will be posting as well, just a sec, on the chat box, so that you can also click the link for this one. Just a sec. Okay, see. All right, so here it is. Okay, so as you can see on your screen, again, to receive your digital certificate, you need to participate in the webinar, stay tuned, and then at the same time, fill out the form, do the survey. We will send you the certificate of attendance. Dr. Peter, any last words before we wrap this webinar today?
No, yeah, I did mention that I'm going to share with the audience a number of papers
Hmm.
that people might want to get more information
Yes,
on. So I'll put it under the
amazing.
checkbox now, and if you
Hmm.
people can take care. So if you are interested in look a lot more in terms of operating envelopes and
Yes,
OPF,
that's true.
you can
Mm-hmm.
go into these free references.
Yeah, exactly. Thank you so much for that, Dr. Peter. And yep, again, so the link, Dr. Peter will be sharing that in the chat box. And again, if you have any questions about it, about our courses, please feel free to reach us here at EIT. And of course, our course advisors team will be happy to assist you with any increase that you may have. Okay. So please feel free to contact us. Okay. You can visit our website at www.eit.edu.au. Our head office is in 6 and 8 Thelma Street, West Perth, Western Australia, and we also have a phone numbers on your screens. Okay, so yep, if you wish to see our available courses, please feel free to just dive into the website and go to the course schedule. Course schedule section, and you'll be able to see all the available courses that we have. And again, please feel free to reach us here. Thank you so much, everyone, for attending. Thank you, Dr. Peter, for that wonderful, presentation and for sharing with us with this information. Thank you so much. And again, this is Marvin, one of the course advisors here. Have a good one. See ya.
See you. Bye bye.
Bye bye.